Right, so far with our stats, we've pretty much just been looking at univariate data, where it's just one piece of information. Bivariate data, so this introduces the idea of scatterplots and correlation. So we're getting two pieces of data from each source. So what we're really interested in when we have that situation is, does there exist a relationship between those two pieces of data that we're grabbing from the same source? And if it is, what is that relationship? So scatterplots are a pretty good way of doing it. Here's an example of one here. Yearly examination results, and these are actual results this time, but no, it's not yours. I think it was from a couple of years ago now, so year 11 yearly ones. But the maths results versus the maths extension results. So the only points we plot are obviously people that did both. Because if they only did maths and not maths extension, you couldn't physically plot a point for them. So we're just interested in the ones that did both exams, what happens. And so we can see there, and the question is, well, do we think there's some sort of relationship between these things? And it looks like, yeah, quite possibly there is there, because it seems to be a nice linear sort of trend. That kind of makes sense when you think about it. I mean, they're very similar subjects, so you do well in one, you would like to think you do well in the other, and vice versa. English is interesting for that particular year. Again, I'm saying it is actual results. When you plot the English advanced versus English extension, I think, whoa, it's not quite the same, is it? It's still it's not as clumped, I guess. It's not as close a relationship as exists with the maths one. And let's do something completely ridiculous. Let's plot the English extension versus the maths extension. And I guess there's no logical reason why there would exist a relationship between the two. Just because you're strong in, say, maths doesn't mean you're going to be strong in English. Mind you, obviously there are some that are strong in both and there are some that are weak in both. Business studies versus maths extension. Okay. And I think the last one I did was PE, wasn't it? Yeah, so PDH-PE versus maths extension. So what correlation is basically the strength of that scatter, how strong a relationship exists, and that relationship, that correlation, will always go between -1 and 1. So unlike probability, because probability goes between 0 and 1, but the reason this goes between -1 and 1 is because you can have a negative correlation. So there might be a relationship, but it might be the case of as one gets better, the other one gets worse. But there's still a direct relationship between the two. Turns out for our first one there, maths versus maths extension, 0.81, and that would be considered a strong relationship. The English extension is a moderate one, 0.49. When you then go English versus maths, there's a weak relationship on that data. And the business studies versus maths ended up being 0.01, so there's virtually no correlation there whatsoever. And the PE and the maths, again, interesting, actually turned out to be a negative correlation. But again, it's a weak relationship, so I don't think it's fair to assume that just because you go good in one, you won't go good in the other on that. All right, now when you're drawing scatter plots, same as any graph, your independent variable should go on the horizontal. But with something like we just looked at, which one's the independent, which one's the dependent, you don't. So it doesn't really matter with something like that, which axes you plot the different things on. So in our course, we're just really concerned with linear correlation. That's what we're going to be looking at. But it is certainly possible to have non-linear correlation. Here's a set of data that I put together, and that has a strong relationship. It's just not linear. That would be a strong exponential correlation. And there's a strong inverse correlation. Theoretically, you could have a quadratic relationship between the data, but really any function you could have. All right, as I say, we're interested in the linear correlation. Now, something you've been doing in, well, not only in maths, but a lot of in science, I would imagine, is drawing these line of best fit. So we want to try and get that relationship between our data. So when we do it, we're looking at multiple points. Now, if there's multiple points with the same data, however, so you might have had two people that got the same results in both, say, the maths and the maths extension. So you'd be plotting that point twice. So when you do it on a scatter plot, you usually identify that point by drawing a circle around it or a triangle around it. But there's some way of doing it. So when you're drawing your line of best fit, you actually know that actually this particular piece of data is more influential than the single pieces, because there's several that landed at that point. So all right, let's go back to our mass versus mass extension. The first way we do a line of best fit is doing it by eye, and we just look at it and we're trying to get it so that it sort of balances evenly above and below the line, so the deviation, if you like, from the line is similar all the way. So that's the one I drew in for that particular piece of data. Now, predictions made by interpolation. Now that I've drawn my line of best fit, I can use it. Interpolation is when I make predictions within the data set that I know. And so for our data set's going from about, 20, maybe closer to 30%, all the way up to maybe 100. But I could interpolate for that. So for example, if I said, let's have a look at 40%. If someone got 40% in the extension test, then I would be predicting that, they'll probably get about 70% based on that data. Extrapolation is then when you predict outside the range of the data that you've collected. See, no one got as low as 20%, but I could predict using this model that, if they did, they'll end up with 60% in that. So that's the difference between interpolation and extrapolation. And a lot of people use the wrong word, but extrapolation is when you're making predictions that's beyond the data that you gathered, the range of the data that you gathered. So correlation versus this other thing called causation. A lot of people make a mistake. Just because you're looking at two sets of data and they correlate doesn't necessarily mean it's true. Right? It doesn't necessarily mean it's true. So for example, here we go. During summer, people get hay fever. There's also a lot of pollen in the air. We know that. So there's a strong correlation between the presence of pollen and people getting hay fever. So therefore, I'm going to conclude from that pollen causes hay fever. And that's fair enough, because people have done studies on this and they've proven that to be true, as opposed to this one. During summer, the sale of ice cream increases, but so does death by drowning. So there actually is a strong correlation between ice cream sales and death by drowning. So from that I can conclude, ice cream must cause drowning. Okay? So that's what I'm saying. The correlation is not causation. When you're using experimental data, the first step is to go, I want to see if there is a relationship. So you do it and you'd say, actually there's a strong correlation. But that's not the end point. You then say, maybe this needs further investigation. I can see it looks like there's a strong correlation, so now I'll go and investigate this. And so like in the first one, people have done further studies and gone, actually, pollen is causing hay fever, whereas I'm sure they haven't done studies on, what do you know? Ice cream does cause drowning. That's not a sensible correlation. They're just both things that happen more in summer. Correlation does not mean causation. All right,